Okay.
So, I mean, the talks yesterday were very clear. This will be not so clear, so so one reason why they were clear is that they were done in a very precise formal system. So type theory with univalence, extended with one data source and 3 axioms. And everything was done in this way, and this can be formalized. So this is very precise. So what I want to do now is to try, still, so one can wonder when has such a formal system and axioms. Is it possible to justify those axioms, and what do they mean? So what does it mean when we do something internally? So that's what I try to say. So it's a justification. Axioms. So of the 3 axioms we say yesterday. So I'm trying to describe the model, a model for this. And so I will start by some reminders of the. This is so yesterday. Felix talked about from PowerPoint. So what was the idea? So it was another presentation of the notion of scheme, and this was actually very early. So in the 60s, it was already there. But so if you take the usual presentation of scheme, then you can look at the scheme S, and then you can look at it as a. So I will fix. So in all these talks, so K will be a fixed commutative way, and it's very important. So there will be K finitely presented ring over K, but it's not the same as what we saw yesterday for the ring R. So that's very important. And also there is so there we look at finitely presented algebra, K algebra. Here we look also at finitely presented R algebra. So it looks like we do twice the same thing. It's very different. So that's okay. But no, so I will consider K, and then to any scheme we can associate a presheaf on the category of K algebra. So K algebra, you take presheaf over this to any, and I will denote by L. So finite K algebra, and for R, I will use the regular ABC. So to any S, so we can look at the K algebra as a scheme, and then we can look at the map of L. We can associate the map from L as a scheme into S. And so in this way, we associate to any scheme a presheaf on this category of K algebra, and this is actually a sheaf for the Zariski topology. So any scheme can be seen as a sheaf for the Zariski topology, and this correspondence is good. So if you have 2 schemes, and then you can look at scheme morphism between S and T. And this is exactly the same as natural transformation between this functor and this functor. Okay. So the idea is to replace, instead of working with schemes as we do usually, we work with functor of points. And this picture is some operations are much simpler here. So there is a notion of product of scheme, which is, quite not so easy to define, but here as it's simply the product of the two presheaf. So it's very simple. Some operations are much simpler on this side. And the same for what is a map between S and T. That's a complicated notion. Here it's simply the notion of natural transformation. So, and this is also what happens internally. So when we do do things internally. So a scheme is simply a type satisfying a property. And the map of scheme is a map, any map between these two types. So that's and the product is a product of types.
Yeah, and it also reflects the name scheme much better. I mean, it has an origin. The name scheme. I mean, it's like a scheme to get solutions.
Okay.
And
yes.
so you
yes.
plug in your coefficient
yes.
ring and then get out.
Yeah, the solution of
the solution set.
Yeah, solution set on this one, yes. Yeah. But sometimes it's not easy to see the semantics. So that's so I want to give some examples. So the example it was what was presented yesterday. So PN. So PN. It's very simple to describe if you work in. So what I said that the scheme is a pre-shift, but actually a shift for Zariski topology. And then, so people have tried to work internally in the first in the topos, one topos of this shift models. And the first was doing it, so it was who had a very simple definition of PN. So it was condensed work. So it said, well, there is a very simple, so internal definition of PN, and that's the one we saw yesterday. So that's so in this collection, so there is R. So and what is R? Is a map which to L associates L as a set. So this is a shift, which is a shift for the Zariski topology, and R inside this topos is a local ring. And then, so one can do things internally. So Pn, as we saw yesterday, so it can be defined as R-1 minus 0, quotiented by the equivalence relations. And this is a very simple internal definition. But if we look at it as a functor of points, so this is actually quite complex. So what is Pn of L for L of K algebra? So it's a set of so sub L modules of L plus 1. So that V is projective expansion. And factor derived in L plus 1. So I will not, say explicitly what it means, but just to say that the definition is not easy like this. And it's very simple internally. But we want to connect the two, and it's not so. Not so easy to connect. So another example where things are simple internally and not so easy externally. So even if you know, so you can define a map for your PM to PM. Internally, it's very simple to define maps like this. So you can so an element of PM is n plus 1 tuple with the equivalence relation. And then, for instance, you can look at this map. So internally, this is what we find. Because if two elements are related here by the equivalence relation, they are also related by the equivalence relation here. So this map is well defined. So this defines internally a map from Pn to Pn. But no, so something which is not so easy is actually, so this should correspond to a functor, natural transformation between these two functors. So if you take V in Ln plus 1, so exercise, that is the image here by this map. So that's so it's not easy to look at the semantics of things in when you have this correspondence. Okay, and so another example that I will present also is that we have been working on with Felix, Matthias, and David is to look internally, so what are this automorphism of PN. So automorphism of PN, so the result is that internally, so this is E GL n plus 1 R. And so what is this? So you can define, so GLN plus 1, so that's invertible matrix. So you have a diagonal matrix if you have so R. So this, and you can take the quotient, and that's so internally it's a quotient of this group, and so the result says that the automorphism of this is these things. But then you can wonder. I mean, I have an internal statement. What is the external statement corresponding to it? So if I define the PN as a scheme over K, what are the automorphism of PN relative to K? And then you have to be careful when interpreting this. So this is not in general. So this is not this. This will not be this group. When you so because you take global section of this, and this is exact, but will not be exact when you take global section. So the automorphism of this is not this in general, but it is if K is local. This is, but K is an arbitrary. So it's not easy. This kind of example shows that it's not easy when you prove something internally, how you can use it externally and what it means. So we have seen R, and this can be defined actually for this R. I can take for base category all K algebra. And if I want a small category, I will fix K algebra for given size. And R, internally, R is a local value. So, but K, as I said, so K is any ring, it may not be local. So, the next thing I want to stress is, something new happens when you restrict yourself to finitely presented K algebra. And that was really the discovery of Ingo Blechschmidt and this synthetic quasi-coherence. Before, let's see. So before going to synthetic quasi-coherence, so something that holds in general, and that was noticed by Understock actually. So it's a kind of external form of this synthetic this duality principle. Still in this setting, so if L is K algebra, we can look at it represents functor, so unit of L. So and since we work with the pressure over K of L, So this is on L. So if L is oh yeah, and yes. No, we always have, so the general statement is, so if F is a preshift, is a preshift actually on K algebra O, F, we always have this, that we can compute this, and this is always, so in the opposite of the category of K algebra, this is like a Cartesian product. So this is, so we always have this. So now if L is finitely presented, and F is R, please, we can look at what happens. So L finitely presented, so that means L is K of x minus L. Oh, no. Yeah. Okay. So what is ohm L? Ohm Lm. Since we don't know of L applies to M, it's actually the solution of this polynomial system in M. So this, and what is yeah, and then if we apply this formula in this special case, so yeah, so actually this is this. So this means actually so unit of L is can be described internally as ohm L. And if we look at so R is the unit of L, so applied to M. Okay, so what is this? So it's L transfer M, R of L transfer M. So L transfer M as a step. Okay. And what is this? So if L is of this form, and this is actually M of x1 itself. Over P1 here. So then you can check actually that the duality principle, so that's R union L of M is the same as L tilde of M, where L tilde is this functor. So L tilde of M is L of X minus M. But this is internally, L tilde internally is R of X1 FM. So that's the essence of why this duality principle follows. And it all in general.
Solid with polynomials over K, so they've got coefficients in K.
Yes, good point. Yes, so we yes, so there is a conversion. So P1, PL are in K, but I can look at them as polynomial in R. And that's this good point. And this is valid. So even if we don't restrict ourselves to finitely presentable K algebras. I mean, for the base category. Here, L was a finitely presentable K algebra, but M was arbitrary K algebra. So now what? So Ingo noticed in this thesis that we can do this. There is something going on if we restrict the base category to be finitely presented K algebra. And so this is a story which can be said in various contexts. So I will describe three examples of this. So one is finitely presented K algebra. There you have so Zariski topology. So local ring, and the things special is that so R is actually represented by P of X, and this is a shield for the Zariski topology. So another example is so that I learned from Ulrich is you can look at the finitely presented distributive lattice. And there you have also something corresponding to the Zariski topology. So Zariski topology is general local ring. So local will correspond to be a linear order. Corresponding to Zariski topology, so you have Zariski topology. I mean, why this is a shift is that to solve a system, a linear system, it's enough to solve it in all co-maximal localization. And you have the same principle for distributive lattice. I mean, to check if an equation hold between take a trivial example. So this equation holds for distributive lattice. I mean, I don't use distributivity here, but this equation holds. And it holds to check that an equation holds. It's enough to check, assuming that you have a linear order. So you can force corresponding to Zariski topology, where you cover here you take a lattice and you cover by you add x is less than y or y is less than x. This notion of covering for distributive lattice, and you have the same phenomena that the generic lattice will be linear. So there you have the generic ring. Is local. Here you have generic lattice is linear. So you can play what I will describe for what we have been doing, synthetic algebraic geometry. You can do it as so Ulrich is doing it for distributive lattice. So another example that so Frank will present tomorrow is so Boolean algebras. And therefore, it's not so interesting if we look on the finitely presented. Tomorrow we'll try to present concavely presented Boolean algebra. And there, so local, what does that mean? It means we have one different from 0, and for all x, invertible of x, or 1 minus x is invertible. And when we work with Boolean algebras for the analog of Zariski topology, so disjoint, finite disjoint covering, what we force is so binary Boolean algebra. So what we will force is 1 different from 0, and for all x, x equals 0 or x equals 1. So what happens that we get bool. That's when we force this. There seems to be, I mean, completely general story that one can make whenever one has the notion of finitely presented or contably presented structure. Okay. And so I know what happens for the what happens is that actually now we can look so in this setting, so now when you work with finitely presented K algebra, you can generalize these inequalities. So now L was supposed to be was coming from an external finitely presented K algebra. Now what you can do is to look at so the theorem is that so you can define the spectrum of L, so now for L finitely presented R algebra. So now L is just this form. So but now those coefficients are in R. Before they were in K. It's only so that was a restricted version of this one. What happens? So that's this. So you have this is actually so L will be isomorphic to R to space. Okay, and this you do by computing. What happens? And the model, yes, and so we are looking for a good name to this principle. So it's a duality principle. And before we called it synthetic equivalence. So no, so I will not give detail, but I want to say so it's not so easy to see what how to make sense of this, because we have to. It's a statement which is quantified over any L, which is a finitely presented K algebra. So the setting of ordinary setting of language of one topos theory is not enough. So in his thesis, so Ingo used what Schulman's have introduced, Schulman's stacks semantics. So it's a generalization of crypto-loyal semantics where you can quantify over all chip. Otherwise, I mean, it's not possible to state this correctly. But instead, so actually, so there is a more general version of this, which is so type theories in which universes. So dependent type theory. can be modeled in any pressure as a model. Pressure model. So there is a good notion of pressure model over any base category. So we can, instead of using the static semantics, we can use this work. So it was done first by Martin Hoffman. And we can use this instead to make sense of this. But this will be done for pressure. So this will be true for the pressure model over finitely presented. You don't need this is true at the level of pressure. Okay. So I want to say, I mean, to check this is not so this is a statement where you quantify over all L's are finitely presented per algebra. So what's the intuition? The intuition is that so L is given at when you do this quantification. So L is not given globally. So may not be given at the level at the initial stage. So it may be given at the stage M. And then we have to look at, but the key is that you can think of this as a presentable, as being presentable at a given stage. So that's why. So the key of all this is very. This is. That you have this formula for exponentiations with respect to presentable pressure. That's this which is the key for understanding this equality. Okay. Yeah, and now we want to understand. So what I want to know is to understand, I mean, how to go from pressure to shift, and what happens for the Zariski local chunks. Well, before going to this, so it's quite interesting. So logically, I mean, the history behind all this, so it's very interesting because there were works going on in algebra in parallel with work going on in logic. So for shift, so that was in logic, so there was bad semantics. That was 54, and that was for explaining intuitionistic logic. And later, so Kripke did also semantics of intuitionistic logic, which is different, and 64. And this corresponds to pre-shift models, and this already corresponds, so he had a notion of like a Gothenburg cover. So this was already, you had the shift semantics. And in parallel to this, so there was a definition by so Algebraic Geometry. So definition of simplicial sets as presheaf. And yeah, it's done in parallel, so they were completely independent, but it was a presheaf model. And there, so later, so there was Zariski focus. And more focus in network. So it's quite interesting that it was yeah, completely independent works, but looking at the same kind of object. So, but so what happened is that actually, so this is not to have one topos, so one sheet model. So it's not enough for what we saw yesterday. So yesterday, so we saw the alternative definition of EN as so sigma so B GM DN plus 1 0. So and this is not the shift, so it's not. So it's not 0 in the language of yesterday. So this is not BGM is not 0 type. 0 type. So we need to model a more complex type than 0 type. And this was not trivial. And so history seems to be so that so people realize that so in order to this kind of object is like a groupoid, and we need 2 groupoids, 3 groupoids, so sheaf that are for groupoid and 2 groupoid. So and the idea was to use so simplicial sheaves. But so simplicial sets, they have so yeah. So I will explain. So what was the problem? So there is a so in order to use this notion, so people have build model structure on this, and it's really important to have to be able to have a Quillen model structure on simplicial sets. And what I want to say is that so the problem is that this was done using classical logic. So when you you develop Quillen model structure on a simplicial set, you use classical logic. So then it's not so clear how to adapt this for simplicial sheaves. And so how to do this in a sheaf model instead. And so that was done by Joyal. He was able to explain how to build a Quillen model structure on simplicial sheaves. But he had essentially to use new ideas to do this. But what we want, actually, since the language of yesterday was dependent type theory with univalence, what we want is, if possible, so a model of type theory with univalence. And so we have been working on an alternative to the simplicial set model. Which is so we talked about so last 2 meetings ago. So typical set model that can be developed constructively, and since we don't use EM in the building in these models, so there will be no problem in going to sheaf models. That's the main idea. So last year, as after actually the meeting we have here, so there have been new development. So Christian, new model of Christian Settler. And this model, so it's similar to simplicial sets, but instead of using only linear order, we use a non-empty cosets. So it's a presheaf of non-empty finite cosets. And Christian was able to show that after a suitable, so technically, so left exact localization of this model, we get actually the right notion of homotopy types. So we get but in a constructive setting. So and that was an issue about those models, but it was not clear how they correspond to the usual notion of higher topos. But with this notion, we get the right notion of higher topos. And so so we are working with Jonas, of understanding, I mean, how to present this model syntactically so that we have a version of time theory which corresponds to this model. So the plan, so this is still work going on. I mean, the plan will be to build a higher topos model of what we saw yesterday, but in a constructive setting, and using this model instead. That will be another presentation of higher topos model for Zariski topos. So I want only to end. So how to go from presheaf to sheaf. And what is nice that this can be done once we have this presheaf model with the right notion of space. Now we can do this translation in a purely syntactical way. So what we want here at the level of sheaf model, so we want R local, and we want N. So this map, canonical map, is an equivalence, and there is local choice. So the idea will be to see what are the properties that are in the presheaf model, and then to do a purely internal sheaf construction to get the actions. And so what are the properties? So this disappears. So in the presheaf model, R is simply a ring. Okay, so this R, which is presheaf, it's a ring. But we have this. So we do have this valid at the level of presheaf. For F finitely presented R algebra. And we don't have a risky local choice, but we have instead something nicer actually. So spec A is projective, internally projective. So in this presheaf model, I mean, we have a choice for spec A. Right. So this is any type over spec A. This is equal as a proposition, it's equal to function x. Canonical map here is equal. And also we can, so natural number, so it's it will be the constant pressure. And we have that, so now expected. The diagonal map is an equivalent, so this is the bijection. So that's the axioms, that's what is valid in the pressure. Okay, so so this is a cell, but this is stronger. So, this is stronger than this. And this will not be valid in the shift model. So how do you go from pressure to shift? And I will end by this. So you that's so simple. So the slogan is that it's simple in theory. To build the shift model. So, what are so you can define. So we want to force. We want to look at the Zariski topology. So we look at the following collection of propositions. So if I have a U1 in R, no, I work internally in the pressure model. And I will, so I will define a type of, so unimodular vector. So it's a vector such that one, the ideal generated by R1 Rn is one. So there exists S1 Sn R1 is one plus and to any vector like this, I associate the proposition. Proposition is invertible for one or invertible for which is, and this is sigma. It's unique. So, sigma S in R, S is one. And what we want to do is to force all the propositions to be true. And so the strategy in type theory is to say that the type T is the chip. And this will be an internal statement, so it's a shift if for any such vector, so the diagonal map like this. Is an equivalence. So to be a shift is a property of the type. Also for any and so this can be defined internally in the pressure model. And what is remarkable is that so shifts are closed by dependent product, dependent sum, all operation of type theory. This condition is stable by all operation of type theory. And furthermore, so more generally, what is not true if you look only one topos. Okay, so you can, so this defines internally a proposition to be a shift. And the remarkable thing is that, and the proof is not, is very, short. Using univalence, you have that collection of all types of archive in itself a shift. And this is true, actually, it's a purely internal statement. Whenever you have a family of propositions, you can consider the corresponding notion of type. So intuitively, T thinks that this is true. So intuitively, in this new model, we found this proposition to be true. Okay. And so this you can do with an axiom. And what you can prove is that the R is a sheaf. So this is provable. And this uses the fact that R, when you have this duality principle. Okay. So what you have is using the duality principle, you have like we saw yesterday. So, this is the same as the localization. So using this, you can show that R is a sheaf. And then, so what happens to the propositional, Zariski local choice? So you can look at, so now you have a new notion of propositional truncation. That's, so with respect to this notion of being a Zariski sheaf, and this is defined, it's possible to, it's the key things is to characterize, to see what this is, this new notion of propositional truncation in this sheaf model, and this is the same as Caesar exists. D1 T. So that's the internal statement which correspond. So externally, what does it mean to have an element of this? Is to have local existence, and they are not necessarily compatible. So I have CT1. Right? So this says that you have local existence of an element of P, but you don't say that there's elements.
So what you also get here is the sheafification of proposition.
Yeah. Yes.
And how to write down sheafification of any type? T?
It's more complicated. I don't. Yeah. So this you don't need. What is nice that you don't need this to say that you have a model. So.
Yeah, but so it could have happened that we have an interesting object like R on the pre-sheaf category.
Yeah.
And which does not happen to be a sheaf.
Yeah. So then you have to do case by case. Yeah, and then using this and using choice, you get Zariski local choice. So Zariski local choice is a consequence of this equation. So, and I will stop. Thank you. Questions?
Thanks to them for the very talk. Many questions were very first. As you mentioned, this sheaf predicate.
Yeah.
It magically is closed under all type moments.
Yeah.
And does this close specifically for the reason that we have a local ring R, or is kind of this type of construction works more generally?
No. So that's what works in general. Whenever you have an internal family of proposition, you can use this. So then you can, but you have to be careful because when you do this, you can get a trivial model. So and there, so you have to check that the model is not trivial. So you have to look at so that's an example actually of sheafifications that you have to do. What is the sheafification of the empty type? Yes.
Okay. And
then it's I don't remember, but you can compute it. Okay, it's a sheafification. So you have to look at for instance.
when it's possible. Maybe another question is that, because you also mentioned the parallel kind of thing, you can do this for finally presenting KR rules, and then you can also do it kind of in logic domains. But for logic, at least to my limited knowledge, there's no kind of real need to go to the higher topos.
Well, so really, I mean, this. So I think you are doing this. Or,
Yeah.
So motivations. No?
Yeah, motivation to look at the category theory and visual spaces, and it's nice to have the larger topos around where you have some representable intervals. So this is visual spaces inside typical spaces based on specific analysis. That has a very nice type theory, and we're working on higher category theory. So they definitely need the structure.
Yeah, so but the motivation is kind of different in two cases. Like on the left, we're interested in kind of Algebraic geometry or the theory of rings, but in finite distributive lattice, you're kind of building a model that is.
Well, you're interested in the generic local ring in the synthetic Algebraic geometry, and for the simplicial case, you're interested in the generic interval, which is what's classified as simplicial spaces.
Okay. Let's see.
Generic linear and bounded distributed graphs. In that sense, it's very parallel.
Let's see. It's just this perspective is kind of different from viewing distributive lattice as propositional theories.
Oh yeah, that's
Yeah.
But it still comes up that if you look at the topology, the sheaf condition for simplicial objects, it's still nice that you have the constructive version of Birkhoff's theory and so on to analyze when things are simplicial. So it's the logic still is in there. The logic is distributed lattice. Leibniz theorem. Finds use even then.
I have another question. So you mentioned that in the pre-sheaf model we have this diagonal map from natural numbers to this like A's and equivalence.
Yep.
What does it tell me for the sheaf model? So why do we mention this?
When you check this, I mean, so when you want to check high-speed local choice, so you have to look at this. And so then you, so this becomes, so you have to look at this. And then you use the choice to go inside, and there it's nice to know that this will become, so what this becomes is sigma it's UN of R with T, you achieve that control. So my feeling was that you need, it's nice to have this because then very implicitly there is a sigma.
Yeah.
And it doesn't change. But yeah, I'm not sure actually if it is. Yeah.
But I mean, externally, it's just the difference between constant free sheaves and constant sheaves.
Yeah.
Free sheaf constant and constant.
Yeah, so the simplification of nuts is not so easy to describe. Yeah. Yeah, I mean, but intuitively, it's N of L. If L is a finite complex Gabellois. So Yeah. So it's classically it's the spectrum of L continuous functions. Into L into L. So then it's given by a system of element in L and natural numbers. So that's another example where you can see what is the signification of constant of a question.
You say we only know this classically.
No, yeah, I mean, yeah, well, it is the
Yeah.
is classical.
Yeah, okay.
This one's.
So, thank you. Okay, so now we have a break until 11.
And there will always be someone doing.
Yes.
Yeah. So maybe we can just say that R is compact instead of duality principle.
Oh,
Like, I mean, we say that R is local. And I mean, as you described that we have this duality principle, that uses the fact that we start with finitely presented K algebras. So it really has something to do with R. Because this is our because this is the option.
but what's the connection with compactness?
Well, so what we have something like on L R and now L is finitely presented. So it's something like a finite co-limit.